Hello there, this is Space Advocate. Space radiation is an issue that many believe is very problematic for missions to and colonization of Mars. Is that the case? Here's what the CEO of SpaceX, Elon Musk, has said.
Sure. I mean, my view on the radiation thing is that there's certainly some risk of radiation, but it's not deadly. There will be some slight increased risk of cancer, but it's I think relatively minor.
Is his opinion on the matter of space radiation accurate, or is it, as some others say, a showstopper for human exploration of deep space? In this video, I will do a deep dive into what space radiation is and how it affects a mission to Mars. The video will be divided into 8 chapters with the timestamps below. If you feel you have a good grasp of the subject, feel free to jump ahead to chapter 7, where I look at the actual expected radiation exposure for 3 different missions. To start off, I want to get some of the basics down. This is a representation of a helium atom. You have a nucleus composed of 2 protons and 2 neutrons, and surrounding it is 2 electrons. Alpha radiation is a helium nucleus that has lost its electrons, while beta radiation is energetic electrons. And aside from beta particles, the most common dangerous space radiation is a single proton, otherwise known as a hydrogen nucleus. Ions are nuclei of atoms that have lost electrons, and nuclei of other atoms can obviously be much bigger than helium, with many more protons and neutrons. These are referred to as heavy ions. Another important term to keep in mind is electron volts. This is a measure of energy, like joules, but it is a very small unit. For instance, it would take around 79 electron volts to strip a helium atom of its electrons. And then I wanted to look a bit at this figure. Many will have seen a similar figure at school. It shows the most common forms of radiation on Earth, which are typically generated by radioactive decay of unstable atomic isotopes. But this is largely not what we're talking about when we're talking about space radiation. Space radiation is not generated by radioactive decay. It is primarily generated by magnetic acceleration of charged particles. Gamma, X-ray, and neutron radiation holds no charge, and as such, it cannot be magnetically accelerated. Alpha and beta radiation holds a charge and is a significant part of the space radiation environment, but they are much more energetic than is the case with radioactive decay. This is to say, unless you've had an in-depth education about radiation specifically, you can probably forget most of what you learned about radiation in school. Space radiation is different. Dangerous space radiation can be divided into 3 distinct categories. The first category is solar radiation, which originates from our Sun. By particle count, electrons dominate, with at least around 10 times the number of other particles. But sometimes, electrons are thousands of times more numerous. For the other particles, it's primarily protons at around 97% and 3% helium nuclei, or alpha particles, as well as trace amounts of heavier ions ranging from lithium up to around nickel, atomic number 28. The particles are a part of the regular solar wind, but by far the most dangerous radiation is released in solar particle events, or SPEs, which are connected to coronal mass ejections and solar flares. SPEs are also called solar storms. In such events, the magnetic field of the Sun rapidly changes, causing magnetic acceleration of particles outwards. The energy of the energetic solar particles is relatively low, mostly in the 1 to 100 mega electron volt range, but in extreme events it can extend up to around 1 giga electron volt. The second category is galactic cosmic rays, which originate outside our solar system. It is composed of around 85% hydrogen nuclei, or protons, 12% helium nuclei, or alpha particles, 2% electrons, or beta particles, and 1% heavier ions, ranging from lithium all the way up to uranium, atomic number 92. The particles have been accelerated to near the speed of light, largely by supernova in our own galaxy, but also by other phenomena. Once accelerated, they are ejected into the interstellar medium, where they remain until they encounter something, such as our solar system. The energy of GCRs is extremely high, starting at around 100 mega electron volts and going up to many giga-electronvolts, even going into tera-electronvolts and beyond. The third category is magnetically trapped radiation. This is charged particles of the former two categories trapped and concentrated by magnetic fields. The most relevant examples here are the Van Allen belts and the radiation belts of Jupiter. The stronger the magnetic field is, the higher energy particles can be trapped and the more dangerous the radiation will become. The outer Van Allen belts trap particles with energies up to around 100 mega-electronvolts, while the inner Van Allen belts trap particles with energies up to around 1 giga-electronvolt. Jupiter's magnetic field is 20,000 times stronger than the Earth's magnetic field, and as a result it is capable of trapping particles with energies up to 100 giga-electronvolts close to the planet. To put the mentioned energies into context, I made this bar graph. But this is with a logarithmic scale, so because people tend to be fairly bad at understanding them, I also want to go through it with a linear scale. Seeing the full picture would be very difficult on a linear scale, so I will add them one by one. First you have a beta particle, or electron, that is generated by nuclear decay. An average particle will have an energy of around 1 mega-electronvolt, which is more than enough to do damage to biological tissue. Then you have an alpha particle, or helium nucleus, that is generated by nuclear decay. An average particle will have an energy of around 5 mega-electronvolts, and per particle, it's the most damaging radiation most people will encounter in their daily lives. Then you have a low-energy SPE particle. These particles will have an energy of around 10 mega-electronvolts, significantly more damaging than alpha particles. Then you have a high-energy SPE particle. These particles will have an energy up to around 1000 mega-electronvolts, or 1 giga-electronvolt, completely outclassing the particles mentioned previously. These are not common, only occurring in the most extreme solar particle events. And then you have a low-energy GCR particle. These particles will have an energy of around 100 mega-electronvolts, which as you can see is less than the high-energy SPE particles, but still quite energetic. Then you have a high-energy GCR particle. These particles will have an energy of up to around 100,000 mega-electronvolts, or 100 giga-electronvolts, which again completely outclasses the high-energy SPEs. And these particles aren't that uncommon, they are a significant part of the space radiation environment. Here I've included the most energetic particles that humanity is capable of making in the Large Hadron Collider at CERN, Switzerland. These particles have energies up to 14 tera-electronvolts. It should be mentioned that equally energetic GCR particles will be encountered in space. Then you have an ultra-high energy cosmic ray. These are particles with energies greater than 1 exa-electronvolt, and they are quite rare. Approximately one such particle strikes each square kilometer of the Earth per year. And finally, you have the most energetic particle ever observed by humanity. It has been dubbed the "Oh my God" particle, with an energy of approximately 320 exa-electronvolts. That's the same amount of energy as a baseball traveling at 100 kilometers per hour. Anyway, that was a little walkthrough of particle energies. What I want you to take away from this is that particles from solar particle events are energetic, but they are nothing compared to galactic cosmic rays. Despite being mostly the same particles, protons, GCRs are something else. This manifests as just being unstoppable. This is a simulation of a very energetic galactic cosmic ray of similar energy as a particle from the Large Hadron Collider, hitting the atmosphere on Earth. The particle is so energetic that it rips atoms apart, and those particles are again so energetic that they can rip other atoms apart. It causes a cascade of secondary particles that manage to penetrate all the way to the surface. That is equivalent to penetrating roughly 10 meters of water. The next important concept I'll introduce is the sievert. This is the SI unit for the stochastic health effect of ionizing radiation, or in other words, it's a unit for the harmful radiation dose received by the human body. The unit is equivalent to joules per kilogram, and it is also equivalent to 100 rem. An aspect that goes into calculating the effective dose in sieverts is the relative biological effectiveness of different forms of radiation. From this table you can see that protons are twice as damaging to tissue as beta particles, while alpha particles and heavy nuclei are 20 times as damaging as beta particles. In other words, 1 joule per kilogram of alpha radiation will do 20 times more damage than 1 joule per kilogram of beta radiation. Another aspect is the tissue weighting factor. This is a measure of how sensitive different organs of the human body are to radiation. From this table, you can see that red bone marrow, colon, lung, stomach, and breast tissue is 12 times more sensitive to radiation damage as skin, bone surface, salivary glands, and brain tissue. Or in other words, 1 joule per kilogram of radiation directed at the stomach will do 12 times more damage than 1 joule per kilogram directed at the skin. However, when talking about whole body radiation exposure, the tissue weighting factor is 1 and can be ignored. The tissue weighting factor matters first and foremost in terms of uneven exposure, like if you stick your head into a Large Hadron Collider. Your brain will be affected by the radiation while your gonads are safe, or vice versa. Still, it's useful to know that not all tissue is equal. Let's move on to the physical effects of radiation. What most people associate with the dangers of radiation is acute radiation syndrome. This will typically occur if a person receives a large dose of radiation in a short amount of time, and it is quite horrible, as portrayed in HBO's Chernobyl.
What does the radiation do to them, precisely?
Ionizing radiation tears the cellular structure apart. The skin blisters, turns red and black. This is followed by a latency period. The immediate effects subside. The patient appears to be recovering. Healthy even, but they aren't. Cellular damage begins to manifest. The bone marrow dies. The immune system fails. The organs and soft tissue begin to decompose. The arteries and veins spill open like sieves, to the point where you can't even administer morphine for the pain, which is unimaginable. Within 3 days to 3 weeks, you're dead. That is what will happen to those boys.
Acute radiation syndrome does, however, require doses exceeding 1 sievert, and that is difficult to accomplish with space radiation. A less obvious but much more relevant risk is cancer. The most common way of thinking about radiation is that there is no safe level of radiation. All radiation you receive will increase your risk of cancer years or decades down the line. Though this hypothesis of there being no threshold is basically impossible to prove. It is entirely possible that the body is able to regenerate damage from low-level radiation without increasing the risk of cancer. Anyway, this graph shows what NASA expects of increased risk of cancer mortality from space radiation. NASA works with a 600 millisievert limit. International partners work with a 1000 millisievert limit. With the current expectation being around 1% increase in cancer mortality per 200 millisieverts, that leads to an increase of 3 to 5%, but still below an average US resident and way below smokers. There are also other effects from radiation that are not deadly. At lower acute exposures, temporary sterility for men is a possible consequence, as well as reduced capacity for production of blood cells, including white blood cells, which are essential for the immune system. The sterility and reduced ability to produce blood cells will recover post-exposure. Cataracts are also possible at low exposures, which is that the lens of the eye can become cloudy. This table sets the limit at 0.5 sievert, but that limit is based on subclinical cataracts affecting vision, but not to an extent requiring treatment. For clinical cataracts requiring treatment, the threshold value is expected to be in the area of 5 sieverts. However, the science here is not completely clear. It's made difficult because of the long time between exposure and the onset of symptoms, at years to decades. It should also be mentioned that cataracts are treatable through routine surgery, replacing the lens with an artificial lens. At higher exposures, permanent sterility is possible, as well as skin inflammation or burns, and temporary hair loss. These conditions are largely treatable if the person survives the acute radiation syndrome that would be likely at these exposures. One more issue that has gotten some attention over the years is neurological symptoms, such as impaired memory and decision-making ability, mood, etc. The idea is that the heavy ions of galactic cosmic rays is different from what most radiation research has covered, and affects brain function more than the dose in sievert would suggest. There are a number of studies that have been performed on mice, rats and primates, and there are also studies from astronauts on the ISS. This is a recent review of a lot of the studies that have been performed on the subject, and it has found that the results from mice and rats largely don't extend to primates and humans, and even on rats and mice, the results are conflicting. So they conclude that galactic cosmic rays are relatively safe for humans.
При ее доброжелательном отношении постараемся из этого взять максимум, чтобы понять для будущего, как женский организм реагирует.
It's relevant to note that the amount of high-energy DCRs received on board space stations in low Earth orbit is for the most part the same as you would receive on Mars, and research from the ISS would be almost completely analogous to Mars. Valery Polyakov is the record holder for the longest stay in low Earth orbit, spending over 14 months on the Mir space station with no meaningful cognitive impairment. His mood was affected by the mission, but it is unlikely to have been caused by the radiation. Long-term effects of GCRs is something that should be studied further, but it doesn't seem to be an immediate roadblock. I also want to look a bit on this table. It doesn't cover every aspect mentioned thus far, but it does cover some of the more important points and provide some meaningful reference points. First, I want to point out the dose of 100 millisieverts. This is the lowest annual dose that has been proven to cause increased rates of cancer. That doesn't mean that there is no risk below this, but it does mean that we simply don't know if there is any risk below this. Secondly, I want to point out the dose of 250 millisieverts. This is an annual dose that some people living on Earth are subjected to from the natural background radiation. Some places on the planet have more radiation from naturally occurring radon and uranium than others, and people live there normally, not offering it much thought. Thirdly, I want to point out the dose of 1000 millisieverts. For a dose that is received in a matter of hours, this is the limit where acute radiation syndrome starts to set in. And for a dose that is received over years, it is the maximum allowable lifetime dose for astronauts from the European Space Agency, the Canadian Space Agency, and Roscosmos. So, just try to keep those numbers in mind when I get to the analysis of how much exposure there would be. A space radiation mostly consists of charged particles. Their behavior is to a large extent determined by magnetic fields. In our solar system, the biggest magnetic field by far is that of our Sun. The magnetic field spirals outwards, and as shown here for a solar particle event, it will carry ionized particles out into the solar system. The Sun's magnetic field drastically affects the amount of galactic cosmic rays. It does this on an 11-year cycle between being strong and being weak. When the solar magnetic field is weak, this allows much more of the galactic cosmic rays to reach the inner solar system, while when it is strong, more of the galactic cosmic rays are diverted away from reaching the inner solar system. As you can see, this causes large fluctuations in the expected radiation exposure. This 11-year cycle also affects the number of solar particle events. When the Sun's magnetic field is at its strongest, that is also when you have solar particle events. So these factors actually offset each other to an extent. You are generally dealing with either a lot of galactic cosmic rays or with energetic solar radiation. I've talked a little about how the magnetic fields of Earth and Jupiter can trap radiation, posing a potential hazard for space travel. But in doing so, they also provide some protection. A common misconception I see is that they stop all radiation and you're perfectly safe close to Earth. And once you enter interplanetary space, or go to Mars, a planet without a meaningful magnetic field, you're subjected to a much worse radiation environment. Well, that is not exactly the case. The Earth's magnetic field is capable of stopping some radiation, but highly energetic galactic cosmic rays go through it like a hot knife through butter. Basically, this means that less energetic, less dangerous radiation, which can also be relatively easily shielded against, is stopped, but it does nothing to the most dangerous radiation, which is also extremely difficult to shield against. This results in the radiation conditions on the International Space Station and on the surface of Mars being fairly similar. Mars has its atmosphere, the ISS has the Earth's magnetic field, and both of these stop lower energy particles. One thing that a planetary magnetic field protects against is a process called sputtering. This is a process where radiation from the Sun can strike the atmosphere of a planet and ionize gas molecules. These ionized particles are charged, so they can then be picked up by the sun's magnetic field and ejected into space. It is thought that this is how Mars has lost most of its atmosphere over many millions of years, molecule by molecule. So it is something that must be addressed for any hypothetical terraforming, but not for colonization. If Mars had a magnetic field, any lower energy ionized particles would be guided to the magnetic poles, where they could be absorbed back into the atmosphere. One of the most important things that can be done to minimize the radiation exposure is to minimize the transit time going to and from Mars. The time spent in space, unprotected by atmosphere, magnetic field or regolith, will have a big impact on the total dose on missions to Mars, particularly short missions. How fast it is possible to get to Mars is something I've covered in a previous video, and I would recommend watching it if you haven't already. See the link above. The thing is, when you're free floating in space, galactic cosmic rays come from every direction. With nothing in any direction, there is nothing to protect you. While on or near a planetary body, 50% of the radiation is blocked by the surface. This effect is increased further by any hills, mountains, massive rocks or sand dunes. Anything extending above the horizon that is at least 10 meters thick will block out all radiation. This is a matter of percentages. If you block out half the sky, you will block around half the radiation. Taken to the extreme, you could live underground, perhaps in a lava tube, a cave formed through volcanic activity. And that is a solution that is very effective. It will block close to 100% of the radiation. However, it does limit you to very specific locations. Locations that may not be ideal for other reasons, like altitude, access to water, ice, metal ore, or geological features with scientific value. And access can be challenging. There could also be challenges with stability. You wouldn't want to get crushed in the cave-in. A compromise could be placing your habitat at the bottom of a canyon or crater with high walls blocking out a lot of the sky. Mars has a diverse geology, including Valles Marineris, which is a canyon that is up to 7 kilometers deep, almost 4 times deeper than a Grand Canyon. Using this as a location for a base would help shield against radiation, particularly if the base is right next to a canyon wall. Additionally, the atmosphere is thicker at lower altitude, and Valles Marineris has some of the highest atmospheric pressures on Mars. Any atmosphere will block low-energy particles like the ones emitted from the Sun in solar particle events. The Martian atmosphere effectively shields against particles with energies below roughly 150 mega-electron-volts, which covers almost all ionizing solar radiation. In this graph, the Martian atmosphere is equivalent to around 10 centimeters of aluminium, dropping the radiation exposure by a factor of around 10. Mars is also further from the Sun than the Earth, meaning that the radiation spreads more thinly before reaching Mars, dropping the radiation by a factor of roughly 2. And the planet shields against solar radiation half the time, which drops it by another factor of 2. Mars, simply being Mars, drops the radiation from a dose of over 3000 millisieverts to around 75 millisieverts, before factoring in the shielding of a habitat or similar. And that is for an extreme event expected to occur roughly every 500 years. One other important aspect is to avoid spending a lot of time deep in the Van Allen belts when leaving and arriving at Earth. But this is something that is easily done, so I will disregard radiation from the Van Allen belts for the rest of the video. It doesn't add much to the total. One additional measure that would help shield against solar particle events and trapped radiation in a lightly shielded spacecraft unprotected by Earth or Mars is to take shelter, using the mass of the cargo for shielding. Starship has the benefit of being massive, so it wouldn't have to be as cramped as this. You would need to shelter for a few hours to a few tens of hours, so you would have to get comfortable. What about shielding against galactic cosmic rays? Some have proposed using water or regolith to shield against the radiation. Piling up regolith could provide decent shielding against radiation, provided it is of sufficient thickness. It does, however, require major construction, which may be difficult without heavy machinery, and you need a lot of regolith. This is how much regolith is needed to stop galactic cosmic rays. You need around 3 to 5 meters of regolith to drop the radiation down to almost nothing, depending on the regolith used and the water content. This figure shows what a Starship modified to be a very protective radiation shelter could look like. you would remove the engines and add an inflatable habitat under the Starship and then fill the lower tank of the Starship with water, and then pile up regolith on the sides. The habitat could be linked to a larger base and be available when needed, for instance as sleeping quarters, cutting down the radiation exposure by roughly a third, assuming 8 out of 24 hours is spent in bed. These are the radiation doses you would receive in different situations during an extreme solar particle event. This solar particle event is a hypothetical worst-case Carrington event of 1859, with energetic particles reaching up to 1 giga-electron-volt. Even so, most of the radiation is less energetic particles, which are shielded against fairly easily. The big risk is if this occurs during an EVA. That would likely result in acute radiation syndrome and perhaps death. The event would, however, last hours or maybe even days, so if you immediately take shelter when it hits, the dose would be significantly less. You would have to continue the EVA for the entire event to get the full dose. And here are the radiation doses for a less extreme event, expected to occur on average every 20 years. As you can see, it wouldn't really be a very meaningful danger unless you're on an EVA. Even the 325 millisieverts would barely result in immediate symptoms, though taking shelter for the duration of the event is advisable. And these are the numbers I'll use for my subsequent calculations. This is quite conservative, as it includes highly energetic, highly penetrative particles that you wouldn't find in most events. The figures are close to a 20-year event every year. Solar particle events on average only occur roughly every 2 years, and they are obviously on average not as energetic. But just to have some contribution by solar radiation, I have included it in later calculations. The Sun is fairly unpredictable. These are the figures for galactic cosmic rays at solar minimum, which is to say these are worst case figures. As you can see, shielding doesn't affect it that much, unless it's very thick. The easiest gains are from simply being on Mars and using the terrain to one's benefit. And this is for solar average. I've used these figures for Mars colonization because you would experience several 11-year solar cycles. You will experience the radiation at its worst and at its best, and the exposure will average out over the full duration. I've set up 3 different scenarios of missions to Mars. They all start out with a Starship flight to Mars. I've assumed the travel time is 4.5 months. This is travel time that is achievable on every launch window using Starship, depending to a degree on the amount of payload. For the first 2 scenarios, which are short missions, I've assumed the trip occurs at solar minimum, which is the worst case scenario for galactic cosmic rays. For the last mission, colonization, I've assumed solar average, as it would span multiple solar cycles. After arrival at Mars, I've assumed for the first scenario that the crew are the first Mars visitors. They arrive at an unprepared site and spend the entire mission living in the Starship they arrived on. For the second and third missions, I've assumed they arrive at an established base or city. Most of the time is spent in an unshielded habitat like a landed Starship, but they are next to a cliff or something similar, reducing radiation. And for all the missions, I've assumed an average of 2 hours of EVA time every day. So, these are the figures I've arrived at for an initial crewed mission at solar minimum. For a 4.5-month travel time, you will receive a dose of 212 millisieverts. That's low enough that you wouldn't experience any immediate symptoms except perhaps temporary sterility for men, but it wouldn't be likely, it would only be possible. For the 17.5 months stay on the surface, an additional 368 millisieverts would be received. That is an average of 252 millisieverts per year, which wouldn't cause any immediate symptoms. And then you have the return, and another 212 millisieverts, and no immediate symptoms, except possibly temporary sterility for men. The total dose is 792 millisieverts, or an annual average of 359 millisieverts. That is within the lifetime maximum occupational limits of ESA and slightly outside the occupational limits for NASA. In the long term, there would be an increased mortality from cancer and an increased risk of developing subclinical cataracts not requiring treatment, but that would be about it. The increased cancer mortality risk from the radiation would be between 2.9 and 4.0%, depending on whether there is a threshold to radiation cancer probability. And then I've looked at a mission profile that assumes there is an established base. You would spend 8 hours per night sleeping in a shielded habitat, and the Starship has been placed right next to a cliff or something similar, blocking radiation from 40% of the sky. The radiation received in transit would be the same. The difference is that during the 17.5 month stay on Mars, you would receive 171 millisievert, or an annual dose of 117 millisievert. That's less than some people experience on Earth. The total dose would be 595 millisievert, or an annual average of 269 millisieverts. That's within the lifetime maximum occupational limits of NASA. And like before, in the long term, there would be an increased mortality from cancer and an increased risk of developing subclinical cataracts not requiring treatment. The increased cancer mortality risk from the radiation would be between 1.9 and 3.0%, depending on whether there is a threshold to radiation cancer probability. And finally, there is the scenario of Mars colonization. This scenario would have a young person travel to Mars and stay there for the rest of their life, which I've optimistically set to 70 years. For this mission, I've assumed solar average. For a 4.5 month travel time at solar average, you will receive a dose of 137 millisievert. That is low enough that you almost certainly wouldn't experience any immediate symptoms. The total dose would be 5,422 millisievert, and the average is 77 millisievert per year. That's of course a much higher total dose than the other scenarios, but because it's spread out over much more time, it's below the 100 millisievert per year level. There would be an increased risk of cancer, both assuming no threshold and assuming a threshold, as some years at solar minimum would have radiation exceeding 100 millisievert per year. On top of that, there would be a significant probability of developing clinical cataracts requiring treatment. So, in the case of a colonization of Mars, there should be a clinic offering lens replacement surgery. The increased cancer mortality risk from the radiation would be between 2.3% and 27.1%, depending on whether there is a threshold. That is of course a very wide range, but there just doesn't exist more conclusive data. This is something that would be a natural area of study once humanity starts spending years instead of months in space. I've shown this diagram earlier, but now I've added the mission scenarios. As you can see, the short missions aren't problematic, and colonization is not problematic if you assume a threshold. While if you assume no threshold, things are pretty bad. Living on Mars could mean having to accept a risk of cancer that is roughly as high as that of smokers. But even if the risk of cancer is that high, I wouldn't say it would be a showstopper. We allow people to smoke, and we should allow people to live on Mars. The important thing is to inform people of the risks. But it is of course entirely possible that there is a threshold, and once we start living on Mars, we may find that it isn't as bad as this. There just isn't any way of knowing until we try and get actual statistics. As I've shown in this video, what the SpaceX CEO Elon Musk has said about the radiation is basically correct. The risk is relatively minor for shorter missions. And for colonization, it is at least not a showstopper, and there is not enough data to say it would be unhealthy. With low effort measures like minimizing the travel time, shielding the sleeping quarters, positioning the base in a good spot on the surface, you can reduce radiation to quite reasonable levels, causing some increased cancer mortality and some increased risk of cataracts. Temporary sterility for men could possibly occur on shorter missions during solar minimum, but it could be argued that this would be a benefit. You wouldn't want any unexpected visitors. Beyond that, radiation doesn't prevent living a normal life on Mars. You wouldn't have to live underground, you could have windows looking out over the surface of Mars, and you can spend hours every day outside the habitat, albeit in a spacesuit. Radiation wouldn't make life on Mars meaningfully different from Earth. The things that make Mars very different from Earth are entirely different things, which I may cover in a future video. Thank you for watching. This video was very challenging for me, with many hours of research and script writing. I hope you found it interesting. And if you want to see more content like this from me, please like and subscribe. It motivates me to keep working on this channel. Or you could give me some constructive criticism in the comments below. Again, thank you for watching and have a good day.